Hello out there. Welcome back to AP Calculus AB. Today we'll be looking at Lesson 3 in our Unit 10, and this is on the volume of solids of revolution by the disk method. So if a curve is revolved around an axis, then it generates what we call a solid of rotation. So the axis of the solid is revolved around is called the axis of revolution. Let's consider the curve y equals the square root of x. For a domain of 0 to 4, revolved around the x-axis, around the axis y equals 0. That's the x-axis. So here's the curve, which has an area, and we could find that area fairly easily, right? And if I revolve this up out of the paper, and then around, it would generate this kind of three-dimensional structure. So here's half of the rotation. So you see I've got some perspective here. So this is my y-axis now back here, kind of coming at an angle, and we're out here in the z-axis land coming out. So we're getting into some three-dimensional geometry there. And then if I continue that rotation back all the way where I started, I create this kind of thimble, or even maybe like a teardrop or a bullet shape, if you will, that's created. So if I were to slice this solid revolution perpendicular to the axis of revolution, what I would get is a circle. So you could see kind of each one of these sectionals is a circle. So the circle would have a radius that is just simply the distance of the curve. See that well, on this curve here, let's see. So that this kind of length here, this is what's drawn around. That's the radius. And so my radius is simply the distance from the curve back to the axis of revolution, which in this case is just the x-axis. So it would have a radius of the square root of x, because that's the y-coordinate right here, which is the distance from the x-axis. The area of this circle then would be pi times the square root of x squared. So each cross-section has that area. Well, if we think about each cross-section as actually having some thickness, a thickness of dx, some change in x, and here's the area that we just described, then we get a volume for this. The volume of any kind of prism or cylinder is area of the base times the height. So the volume of each one would be pi r squared, which we said was this. We could call that just x, because the square root of x squared, times the height, which is simply dx. And the height is actually moving left and right as along the x-axis. Then the integral expression for the volume of the solid is the integral of pi square root of x squared dx from 0 to 4, since we said we were going to look at it over that domain. Typically, you'll see people write the pi on the outside, but it's simply area of the volume of the cylinder is pi r squared times h. So their area similar is pi, the sum of all my r's squared from 0 to 4 times the height of each cylinder dx. Okay, let's take a look at another example. This time the region R is bounded by 4 minus x squared, x equals 0, and y equals 0. And a solid of revolution is formed by rotating R around the axis y equals negative 2. So again, here's this region, and we know how to find the area of that pretty easily. But now we're looking at rotating this region around this axis of symmetry. But see this gap here? This gap is going to continue as well. So we have this outside portion that's rotating out, but this inside portion is rotating as well. So our figure is going to have this hollow base. Can you see here where this distance, because our axis of revolution is lower below the x-axis, this gap here is creating this empty space. So there's it under a full revolution, and you can kind of see it from the inside. So in fact, each one of our cross sections will really have an outer radius where the volume begins, and then another inner radius where the volume ends. If that makes sense, if you can see that. And those are often called washers. So we say each cross section is a washer. I usually just call them discs or anyway, but they now have a hollow center. And we simply are going to be finding the volumes of cylinders and then cutting out the middle. So the area of one of these washers is going to be a big R minus the area with a small r. So then the volume of one washer that's dx thick is pi r squared minus pi r squared. And then each one of these gets a dr. So the volume of the solid is pi r squared dr minus the integral of pi r squared dr. So we get the volume of the big outer solid minus the inner solid. And we'll be doing this from, let's see here, we're doing this from, well, wherever the graph hits the x-axis, which is actually at 2. So from 0 to 2. And we know that our r is this outer r, this outer radius is the length from the curve to x minus 2. So it's this length here, which is 4 minus x squared. That's the y-coordinate here. And the y-coordinate down here is a negative 2. So minus a negative 2. So for the distance from here to here, the distance between 2 points is you subtract their coordinates, right? So this becomes actually 6 minus x squared. The inner radius is 0. That's that y-coordinate. Minus 2, or minus a negative 2, or simply 2. So this is the integral from 0 to 2 of pi times, we said 6 minus x squared, pi r squared, dx, minus the integral from 0 to 2 of pi little r squared, which we said was just 2, dx. Oh, I wrote dr here. I'm sorry. I should have called these dx's. All right. So then I want to show you how this is usually written, though. Instead of separating it, you'll usually see most people describe this formula as pi r squared minus r squared dx. So this would be, if we write it in that form, pi times the integral from 0 to 2 of 6 minus x squared minus 2 squared dx. So that is how you would find the volume of that solid. Okay. And I'm just writing the integral expression on these. I don't think we need to go and actually plug it in and find it out right now. All right, let's look at example 3.3. A region R is defined by the curve y equals x squared, the x-axis, the y-axis, and the line x equals 4. Find the area of R working with x and dx. So I can find the area of this R, this is the part of the curve under x squared, between the curve x equals 4 and the y-axis. So that's pretty simple. I would just take the integral of x squared dx from 0 to 4. I could also express it in terms of y's. I could be taking rectangles this way. So if I work in terms of y's, I'm going to need to solve for this is y is a function of x. So if we solve x squared equals y, we get the square root of y equals x. Technically, we get plus or minus, which, but I can ignore the negative because we're only in the first quadrant here. So I have x equals the square root of y, and I need to express this distance here from here to here to find the area. This is a 4 for an x-coordinate, and this is the square root of y. So this is the integral from 0 to 16, the y-coordinate 16, of 4 minus the square root of y. If we just did the square root of y, we'd actually be getting this area to the left, in between the curve and the y-axis, but we want the area in between the axis x equals 4 and the curve, so I have to subtract the two. And let's go ahead and integrate this. This evaluated the 64 over 3. Let's go ahead and evaluate this one just to make sure. So we get 4y minus y to the 3/2 times 2/3 from 0 to 16. So 4 times 16 is 64. And then I have to do 2/3 times 64 to the 3/2, which is, 16 to the 3/2, which is 16 to the 3/2 is 4 cubed. 4 cubed is 64, times 2 is 128. So I have 64 minus 128 over 3. And 64 times 3 is going to be whatever 128 plus 64 is. What is that? Let's see here. That's 192, I think. So it's 192 cubed minus 128 cubed, which is 64. Excuse me, 128 over 3, not 128 cubed. 128 over 3, 64 over 3 is the volume, which was the area, which was the same that we got here working with x's. Now, what if the region y is rotated around the y-axis? Let's find the results of the volume of the resulting solid. Well, you can see if I'm revolving around the y-axis, I have a washer, but my height of my washer, the height of the cylinder within the cylinder, is actually dy, because we're now, anytime we're revolving around a vertical axis, we need to be working in terms of y's. So we need to find this representative washer, right? This representative washer is going to have a height of dy, an outer radius from the axis of revolution to the far right point is actually 4, because we're revolving around the the y-axis, and this x-coordinate is 4 from here to here. The inner radius is going to be simply the square root of y. So we have the integral from 0 to 16 of pi r squared h minus pi r squared h. So pi big R squared minus little r squared times the height dy. All right, the volume R is rotated about the x-axis. Draw a representative washer. Write an expression for volume. Use your calculator to find the volume of the resulting solid. So if we rotate it around the x-axis, remember we had this as our region. So to rotate around the x-axis, my outer radius here for my shape is simply the curve, which we said was x squared. And there is no inner radius because this is flush right against the axis of revolution. So there's just one radius. So we're really using disks here. So pi r squared, so x to the 4th, dx, and then I'm going from 0 to 4. All right, lastly, the region R is rotated about the line x equals 5. Draw a representative washer, write an expression. So this case here, we have this curve. This was x equals 4. Now we're reflecting around x equals 5, rotating around x equals 5. So we're going to be rotating this way. And my washers are going to have an outer radius like that, and then an inner radius like this. So my outer radius is the distance from the axis of revolution to the furthest point away, which is the curve, the square root of y. So my axis of rotation, 5, minus the square root of y. You might think it's the square root of y minus 5, but we really should start with the rightmost point minus the leftmost. It wouldn't really matter if you get it backwards, since we'll be squaring it anyway, getting rid of any negatives. All right, then my inner radius is from here to here. That's just a radius of 1. So my integral is pi r squared minus r squared. So 5 minus the square root of y squared minus 1 squared times height dy's. All right, I got some practice problems for you to do. Practice 3.1, A, B, C, and D. So pause the video, please, and give that a shot. All right, let's see how you did this one. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals 9 minus x squared, x equals 0, and y equals 0 about each of the indicated axes. Sketch the region and draw a representative washer. So 9 minus x squared looks like that. We have x equals 0, which is actually this line, excuse me, and y equals 0. What if I was to revolve it around the x-axis? That means we're revolving this way. The entire region is completely flush with that axis rotation, so I'm just going to have a disk here. So it'll be the integral from 0 to, you could solve for this x-intercept, 3 comma 0. So from 0 to 3 of 9 minus x squared squared. So remember, it's pi r squared h, and then our h is simply dx. That's our representative washer is being made vertically. Whoops, there's no center, so it's just from here all the way up 9 minus x squared. All right, what about the line y equals -2? Let me grab this image here. So we need to use y equals -2. Well, that's not quite the x-axis. That's down below a little bit. Somewhere down here. And so we're going to have this open space where our region was not going to be swept, because this is going to come all the way out here, and this is going to come all the way out here. So my inner radius is this length here, which is just the height of 2, 0 minus a -2. And this height, the outer radius, is 9 minus x squared minus a -2, which comes +2. So it's 11 minus x squared. So my formula will be pi times the integral from 0 to 3 of outer radius squared, which is 11 minus x squared squared minus inner radius squared, so minus 2 squared dx. All right, next, let's talk about the y-axis. What would it be if I used the y-axis as my axis of revolution? Well, if I'm going to do that, I need to solve this equation for x. So I can work in terms of y's. So rotating around the y-axis is rotating around like this. Notice that the region is entirely flush with the y-axis, so we will just be using disks here. All right, so solving 9 minus x squared equal to y would give you x is equal to 9. Let's see here. Minus y square rooted. Since we're in the positive quadrant, we'll just take the positive square root. So I need the integral of r squared times pi r squared times h, which in this case is a dy. As my washers are thin like this, dy, and this length is 9 minus x squared. Now, what about the line x equals -2? Well, here's our curve again. Oh, we forgot to put the bounds on the previous one. I'm sorry. My bounds are actually 0 to 9. That's the y-coordinate up here where the curve ends. So the line x equals -2, if we're going to rotate that, then again we need this inner radius that'll get rotated around, and then an outer radius that will get rotated around. So the outer radius is going to be 9 minus y square rooted minus a -2, so +2. My inner radius is just going to be 0 minus a -2, so just 2. So pi r squared minus r squared dy. All right, practice 3.2. The graph at right shows f and g for 0 to 4. R is the region bounded between f and g. S is the region bounded between g and the x-axis. The area of S is 5.120. I would like you to write an expression and use a calculator to evaluate the area of R. All right, let's see how you did. So to get the area of R, that's the area between two curves, right? Not too bad. Let me get a copy of this picture. Oh, Drew a line right through it. And I'm just going to bring that down here a little bit. Give myself a little bit more room here. There we go. So to find the area of R, I need to take the y coordinate here and down to the y coordinate here. And then that would be my base of my rectangle, if you will. And then my height of my rectangles I'm using to get the area are going to each be dx. So we need the integral of, what is the blue curve's equation? The blue curve's equation is negative 1.2x squared sine of negative pi over 4x. Sine of negative pi over 4x. Minus, so dx minus the integral, and that's from 0 to 4. The integral from 0 to 4 of S, of the region S, which is, I'll just call it g of x, because I don't know the equation for g of x. But we were told that the area of S is 5.120. So you'll notice I wrote this split up, not combined, and I did that for a reason. .120, because that definite integral is the area under that curve. So now we can use a calculator, and we'll take the integral of negative 1.2 x squared times the sine of negative pi over 4 times x, comma x, comma 0, comma 4. Then I'll just subtract 5.120. And we get 9.419. All right. Letter B. Given that the integral from 0 to 4 of g of x squared dx is 10.4, find the volume of solid found by revolving the region R around the x-axis. So again, let me get a free picture, another copy. So let's see, I'll grab this, and let's put it right here. Oh, well, hold on. Need a little bit more room here. I'm going to do that. All right. So we were given the integral of it squared, so we're probably going to need that as well. The integral of g. This is, remember that this is f up here in blue, and then g is down here in purple. We want to find the volume from revolving this region around the x-axis. So I need to find that outer radius minus this inner radius that is going to be revolved around. So the integral will be from 0 to 4. The outer radius is negative 1.2x squared sine of negative pi over 4x dx. That is squared. Well, I don't need the dx yet. We'll wait and put the dx at the end. That is squared minus the integral of g of x squared. All that times dx. Well, I can use properties of integrals, though, to split this apart from 0 to 4. Negative 1.2x squared sine of negative pi over 4x squared. I'm thinking that's a negative pi over 4, right? That's what that was. Yeah. Minus the integral from 0 to 4 of simply g of x squared dx. Well, they told us that integral was 10.4, so I just need to use a calculator to do this one. So the integral of negative 1.2 times x squared times the sine of negative pi over 4 times x squared, comma x, comma 0, comma 4. And then we're going to subtract 10.4 from that. And what do we get? Well, it's chugging away over there. Now we have to wait and come back. All right, well, never mind. I got tired of waiting. It seemed like this calculator was not going to figure it out. So I went back and changed. I hit enter on to break it, and then went back and changed it to a numerical integrate. And I got the answer pretty quickly. So we get, and you can see what I typed in here. We get 73.707 for our answer. All right. That's not a negative. It's a part of an equal sign. Okay, next. Given that the integral of... Oops, it's telling me to update my computer. Given that this... the integral from 0 to 4 of g of x squared dx equals 4, find the volume of the solid formed by revolving the region R around the line y equals negative 2. Okay, so once again, let me get another picture, but this time we're going to revolve around y equals negative 2. So, something down here, right? So, when I revolve it around there, this is my outer radius, which is negative 1.2x squared times, was it sine of negative pi over 4x? I think it was. Minus a negative 2, so plus 2 squared. And then I got to subtract the integral of g of x minus a negative 2, so plus 2 squared dx. And we're going to be doing them both from 0 to 4. And I'll just go ahead and split it up. We know we need to, so I'll put a dx here. So I've got to split this up. This we can do on a calculator. This, though, we need to go ahead and do some simplification. If I expand this g of x plus 2 squared, I get g of x squared plus 4g of x, because multiply g of x times 2 and double it. And then plus 4 dx. And then I can split all of this up and get negative the integral from 0 to 4 of g of x squared dx minus 4 times the integral of g of x dx plus the integral from, or minus the integral from 0 to 4 of just 4. Well, we were told all this information. We were told that the area S is 5.120. We were told that part. So this is simply 4 times 5.120. This is just a rectangle with a base of 4 and a height of 4, so minus 16. This here is, we were told, is 10.4. So I just need to do this integral minus all of those things. Let's do that. So I'll be using a numeric integrate again. So I've got negative 1.2 x squared times sine of negative pi over 4 of x. And all that is squared, but I'm going to add a plus 2. And then at the end, I'm going to do minus 10.4 minus 4 times 5.120, and then minus 16. And hopefully we get an answer relatively quickly. We get 111.381. And there we go. Okay, so I hope you found that problem kind of interesting, how that would work out. And that is it for this lesson.